that it is the assignment that have been given, except the last problem, which is a reasonably large assignment with multiple modules. The other assignments are all single module assignments, so they are very, very simple. Okay, and if you follow the general principle that I am going to describe for FSM design in Verilog, if you stick to that, the chances of you making mistake will be minimized, and it will be quite easy. So I'll start the recording now, and I'll share the screen. Oh, it is already being recorded, I think. The recording is happening, right? Okay, somebody has already started. Good. Let me share the slide. Yeah. So I hope you can see the slide, modeling finite state machines. And we will start with this. Find the, yeah. So this set of slides, this is a PDF. This has been uploaded already on Moodle. Okay. So you should find it. It has already been uploaded. There are 2 tutorials on Verilog that have been uploaded. This is one of them. From your study, from your previous course on switching circuits and logic design, you know that there are 2 types of finite state machines. One is called a Moore machine, and the other is called a Mealy machine. The Moore machine is the relatively simpler one. In this, if you look at the output value, the output value is a function of only the present state. Okay, so here the NS signal means the next state, the PS signal means the present state, the FF is a collection of flip-flop. Okay, so these blocks is a collection of flip-flops, more than one flip-flop possibly, depending on how many flip-flops states you have in your finite state machine and what is your state encoding. The number of flip-flops will vary. So this one is purely sequential. This one is purely combinational, and along with that there is a next state logic block which is also purely combination. Okay, so what does the next state logic block generate? Well, it generates the next state value depending on the present state and the incoming inputs and makes it ready for the clock signal to come. And when the clock edge comes, active edge, depending on whether it's a positive edge triggered flip-flops or negative edge triggered flip-flops, that value is sampled and the output present state value is updated. So essentially the signal that has not been shown here is a clock signal. Okay, and along with that, I suggest that you should always add a reset signal to your flip-flops. Okay, always have it in your flip-flop. Do not describe any flip-flop or any sequential logic part without a reset signal, because if you do not have a reset signal, the initial state of your flip-flops is not defined, and that can cause many problems. So with a master reset signal, you can force the flip-flop to go to a known state. The Mealy machine is slightly more complicated, because in the Mealy machine, if you look at the output logic, it is a function of both the present state as well as the input. Okay, so in the Moore machine, you could have probably written that the output logic in an abstract sense is a function of only the present state, whereas in the Mealy machine, your output logic is a function of both the present state as well as the input. Okay, so this is your basically input values. That's it. And similarly, this in the melee machine also, the output logic block and the next state logic blocks are purely combinational, and the flip flop, the block that has been shown to be flip flops are purely sequential. Of course, these also have this uh, clock signals and reset signals, etc. Okay. Why suddenly the finite state machines have been shown in this fashion? Well, they have been shown in this fashion because if you do that, your description of the final state machine becomes very, very simple. Okay. How can it become simple? Let us have a look. So you should kind of memorize this diagram. Okay. I mean, this diagram is fundamental in understanding how you are going to describe finite state machine. So let's see, what does this mean? So for melee machine, okay, let's start with Moore machine because that is the easy one. So for the sequential part, okay, and okay, so the sequential part for the Moore machine and the melee machine are both are both the same. So we can they are exactly the same. What is the sequential part? Suppose you have four flip flops. Okay, so I'm saying four flip flops because in one of the assignment, the first problem, you will find there are four flip flops. Okay, so four, there can be one flip flop, two flip flops, four flip flops, 10 flip flops, whatever. So you somewhere you must be having somewhere you must be having some range 3 to 0 say state. So name of my flip flop registers is state. Okay. Then you write the clock logic. Okay. So you write always at the rate, say it is a positive edge triggered flip flop. Uh, and say a positive level sensitive reset. So if reset, your state becomes 0 and we use a non-blocking assignment. Okay, because this is sequential circuit. Else, uh, okay. So instead of the state, let me call them PS and NS. Let me follow the same convention that they have used, naming conventions that they have used. So this is classic D flip flop behavior uh, with an asynchronous positive reset. Okay, why this is asynchronous reset? Because it gives equal importance to the reset signal as well as the clock signal. In fact, it gives more importance to the reset signal that the flip flop can be reset anytime asynchronously. How could we have turned this to synchronous reset, students? Anybody? Hello?
Use asynchronous or synchronous?
This is asynchronous. I am asking how can we, if you wanted synchronous reset, how can we do it? Synchronous reset is a reset that happens at the clock edge, at the active clock edge. So how can we do it?
We can have a control signal and then check if the control signal is zero.
No. It's not required.
So we
Synchronous
can
reset. Yeah,
we can
tell me.
just remove the postage RST in the.
Yeah, exactly. So we could have just removed this part. And this would have become a synchronous reset, because now this is called the this is the kind of the list of parameters to which it responds. The event changes happen at this list of parameters. Okay, this is called a sensitivity list. In my sensitivity list, currently there is only one event, that is my posage clock. There is no other event that can control the flip flops. So if the posage clock happens, I check the two different conditions. I kind of, in programming language or C terminology, you say you entered the block. You entered the block of code and check. Then there is a if else clause. And then if reset is true, the flip flop is reset. If the reset is not true, then it updates the state by copying the input value to the output value. Okay. But here, I generally prefer asynchronous reset. There is no, as such, there is no reason to prefer it. I mean, you can use anything, but whatever you use, you stick to that in your design. Do not use two types of flip flops. Use either asynchronous reset entirely or synchronous reset. In terms of hardware design, I think both asynchronous reset flip flops as well as synchronous reset flip flops are either directly or indirectly supported in FPGAs. Synchronous reset flip flops are relatively easier to design. Asynchronous reset flip flops might be slightly more complicated, but anyways, I mean, both can be used. Okay, and you can use any of them. Just mention what convention you are using. So I am sticking to asynchronous reset. Fine. So this completes my sequential part for any Mealy machine or any Moore machine. Okay. Any question about this? Any difficulty in understanding this, students? See how simple it is. Okay. So you completely kind of disintegrate the design into three separate parts: a present state logic, a next state logic, an output logic, and sequential logic. So this sequential part is done. So let us now move to the uh, NS logic. What is the NS logic? If you remember the diagram, the NS logic is the combinational logic which controls the so this was the NS logic. So NS logic is the combinational logic that controls the next state generation. Okay. So let us now consider this. This is purely combinational. Okay, and again it applies for both Mealy machine as well as Moore machine. So because it is purely combinational, there are many ways to describe it. Structurally, data flow wise, behaviorally. I am showing the behavioral description using always block and blocking assignment statements, so that you want, you can basically describe your entire design using always block. It's not essential, but for simple state machines, you can describe your entire design using always blocks, as I will show in some of the examples in the slides. The way to describe combinational logic using an always block is to write always @star. When you write @star, this basically means that all signals in the sensitivity list and combinational logic is inferred. So there might be many statements in an, there can be many statements. There can be multiple always blocks also in your design. No harm. There can be multiple always at the rate start blocks also. There can be multiple at the rate sequential blocks also. Just depending on the context, they should be correct. Okay. For example, two signals cannot be the on the left hand side of two different always blocks. Okay, means you cannot drive multiple signals onto a same signal. Those kind of things does not happen. But eventually, what happens is that n is equal to say some function f of the present state and the input. So here I am writing everything in one line. Of course, this won't be that simple because there might be many different equations that you might need to write. Many defined assignment statements. Notice how I have used combinational this blocking assignment here. Okay. Because this is combinational logic. Fine. Now, my next state logic is gone, is done. Then comes my output logic. Well, what is my output logic? My output logic for now, there are two different cases. For the Moore machine, my output logic is a combinational block, which is a function of only the present state. And my Mealy machine is an output logic, which is a function of both the present state as well as the input. Okay. So this has to be remembered and accordingly correctly coded. So again, because it's purely combinational, you again write the output equal to some function g1 of present state for Moore. Okay, so let me write it in a slightly different way. I think that will be less confusing. So I consider two cases. Okay. One is a Moore. Here I write that the output is just a function say g1 of the present state. Sorry, that mistake of the present state. And that's it. Okay. So I have implemented my present state next state logic using a simple sequential circuit. If you see like this with a reset signal, I have implemented my next state logic as a combinational block, And finally, for the output logic, there are two different cases depending on whether you are implementing a milling machine or a Moore machine. You have to implement one of them. Okay, and that completes your design. So as you can see, it is so simple. If you just stick by these rules that I am going to use, and again, uh, again, you should notice that I am using blocking here, blocking here, and I had used non-blocking here. If you stick by this design template, the chances of you making mistake is very less. Okay. Any question about this, student? Anybody has any question? Otherwise, I will move to some examples of this design principle. In some very simple circuits, you will find that the next state logic block and the output logic block are merged in the same always block. Okay, means these are merged. That's okay, but if you want to keep it even simpler, you can just have separate logic blocks also. It's up to you. Okay. Any questions, students? Okay, if there are no questions, let me move to the slide. So let's see some examples. So there are some nice examples. You should have a look at them. For example, there is a traffic light controller. Okay, it's a Moore machine. Uh, and unfortunately, unfortunately, all of these examples, example 1, 2, 3, etc., they all of them do not follow the design principle I just mentioned. Most of them merge everything into one block and makes it difficult to understand. So let me move to one example. I think there is where exactly this design principle has been followed. Okay, there is a serial parity detector circuit which keeps on reading a bit stream and output 0 for even and output 1 for odd, and continuously keeps on updating it depending on how much of the bit string it has read. So the state diagram is this type of finite state machine design you have done many times in your flat course, as well as probably your switching circuits course. Very simple. But again, if you look at it, they have merged everything. It's perfectly fine. These are correct designs, just that they are not following the uh, principle that I just now mentioned. Now, this is on slide. Okay, the FSM example started from slide number 69. Okay, so page number 69 of the PDF. This example that I am speaking of starts on page number 79. This is a nice finite state machine. It tries to detect the pattern 0110. Although not much description is given or detailed description is given, if you analyze the code, you will find that basically it is trying to detect an overlapped pattern. Okay. S1 is the accept state here. Okay, so this one is basically the accept state, and overlap patterns are allowed. Okay, so some examples. If it is your input bit stream this machine also reads one bit at a time, and this is the start state which has not been shown. Okay, if your pattern is say 0110 110, then it will detect two matches because it is allowing overlap. Uh, 0110 here, one match in this, and in this entire thing there is no match. Fine. So this is basically essentially a flat uh, wave detector exercise that we have done in flat. The only thing is when you write, when you write the or when you draw the state diagram, you have to maintain certain principles. This is the way you draw the state diagram of a milli machine. In this, you write the symbolic states, connect them with arrows, and for the transitions, you write the input that causes the transition and you write the corresponding output. So this is the input and this is the corresponding output after a slash symbol. So these are very basics. You must have been taught this when you studied your digital logic course. And the notation that is used is not exactly similar to your flat state diagrams notation. Okay. When you are drawing FSMs for circuit implementation, you should follow this type of notation. So this is a classic milli machine. If you are looking at a Moore machine, the state diagrams will look slightly different. In the Moore machines, the states like it has not been shown here, but basically the states themselves say in a Moore machine say the state S1 should output 0. So you and if S1 is the state, you show it inside the state, and there is no uh, flash on the edge. Okay, so you write the output inside the state symbol itself to show that it depends only on the state. Whereas in this case, your output depends on both the present state, which is S0, say S3, as well as the current input 1. So we add S3, if it gets 1, it transitions to S0 and makes the output 0. This is the meaning of it. In state S0, if it receives a 1, it keeps on self-looping and it keeps on outputting 0. Okay, so this is the meaning. So we have 4 states. I need to assign symbolic numerical values to these symbolic states. So you can do it using the parameter statement of Verilog. Okay. Note that these are decimal parameters. I would prefer if you write it in instead of S0 equal to S3 equal to 3, if you write it explicitly to be excuse me 2 tick B 1 1. This one instead you write to be 2 tick B 1 0 to show that each of these uh, symbols actually is 2 bit. This will also compile fine, no problem. But just to be more precise, I would have probably. Now they have because there are 4 states, 2 flip flops are sufficient. So they define a register, uh, PS and NS, just as that I shown, and it's a 2-bit register. Notice that here for some reason they have reversed the indices. More commonly, I would have probably used 1 to 0. They have used 0 to 1, doesn't matter here. Uh, unless you are dealing with numbers and sign bits, etc., this doesn't matter. Anything you can use. The output is a single bit. This is the output that shows whether the pattern has been detected or not when it reaches the accept state. And of course, it has 2 input signals, X and clock. Any input signal, if you remember, is of type where. Mandatorily, output can either be of type where or of type range. By default, it is where. but you should explicitly write output where or output range. That is what modern Verilog compilers insist. If you do not write output range or output where, if you just write output, it will compile, but if you it will give you a warning that for this signal, the nature of the signal was not mentioned, or nature of the port was not mentioned, so where was inferred. But be very careful. I would suggest always write output where or output range. So these guys have decided that this is going to be a range type variable, not necessarily range type variable. It means it will have a flip flop. Depends on how it has been implemented. Probably they have probably they have written it to be a range type variable because they are going to include it inside an always block where z is going to be on the left hand side. Okay, of any assignment statement. If any variable is in the left hand side of an assignment statement in always blocks, they must be of type range. Okay, doesn't matter whether it denotes combinational logic or sequential logic. So please remember this. First is the sequential logic part. Okay, no reset signal is there. This is kind of bad design practice, so I would have probably added a reset signal here. And added the if blocks, if reset, yes to tick b0, else, etc., etc. I would have probably written it in this way. It this guy, there should have been another reset signal here. There should have been another reset signal here, etc. So essentially, in your state machine, this start happens by having a reset. Okay, so when reset equal to 1, it goes to start as 0. In your when you in the flat course, when you are designing sequence detectors or any DFS, there is no answer to the question how did it reach the start state. There is an abstract start state, fine, but how did, if you implement the machine, there in software or in circuit, how did it reach the first state? Is nobody asked this question, but of course, since we are designing circuits, there should be an explicit reset signal to force it to go to the start state at any point of time. Notice that this reset signal is very powerful in a sense that as long as the reset signal is held at 1, it remains on here, and all of these have self loops. All of these basically have not self loops. They have, all of them have loops back to this start state. At any point of time, you can reset the signal, reset the state machine. Anyways, that's fine. Now the combinational logic part, here it is NS logic and output logic are combined. So in one always block, they have written the NS logic and the output logic. And they have used a case statement. Fine, you can use a case statement. You have to look at the state diagram, say for S0. If for S0, if the current state is S0 and my input is 1, I go to S1, I keep the output 0. If my input is 1, I self loop and keep the output 0. So how have they coded it? The case statement depends on the present state variable. If it is S0, there are 2 assignments. So they notice this begin end statement. These are necessary because there are 2 assignments inside one clause. So if it is in state S0, output is the input. This is the input. Remember, this is the input. Don't confuse it with X. which is the unknown symbol in unknown variable value in Verilog. Okay, this is an input. So if the input is true, it is 0, and if the input is true, it is S0, self loops, otherwise it goes to S1. Exactly the behavior we saw. The state machine. In this way, you can complete this. And that's it. After the end case ends, uh, I I usually like to add a begin end, even if it is redundant for always blocks. Here there is only one single case statement, so that is not necessary. Means it will be a redundant begin end statement, but I would rather add a begin end also. It is end always. And finally, you end module and your circuit is done. Okay, extremely simple template. Basically, the skill lies in coming up with the finite state machine diagram, because there is no algorithm to automatically generate you. I mean, somebody asks you, design me a finite state machine that will detect this sequence. It requires little bit of creativity, okay? Little bit of maybe trial and error. Once you get some practice, you will do it very fast. Uh, this must be a quite simple exercise for you, that because you have taken the flat course already. But once you come up with this and once this is correct, implementing it in Verilog, if you follow the template, is not very difficult, as you saw. Any question about this, students? Anybody has any question? Students, are you there?
Yes, sir.
Okay, anybody
Yes,
has
sir.
any question? Are you understanding what I am teaching?
Yes, sir. Yes.
Yes,
Fine,
sir.
fine. Now let us move to today's assignment, okay? Okay, so we will allow 1 week. Time allowed 6 hours is given because essentially it is for 2 classes, but you ignore that. I have already released this on Moodle, and I have set the deadline to be exactly 1 week from now at 1:55 p.m. of next Wednesday. Okay, so you have sufficient time. There are 4 problems. So 4 might seem to you there's a lot of problems to solve, but actually they are quite simple. Let me start with the first one. The first one is about the design of a linear feedback shift register, or LFSR. LFSR are very useful, simple but very useful circuits with amazing mathematical properties, used all the time in data communication, cryptography, random number generation, and many other digital circuit design and testing, etc. I mean, as a digital circuit itself, it is very useful and interesting, but its mathematical properties are also amazing. Those of you who take cryptography course later on, or might be taking now, might have been introduced to this thing in the form of pseudo-random number generator or PRNGs, which are also another form of LFSRs. The LFSRs, why are they very attractive? Because you can implement them essentially using only D flip-flops and XOR gates. In this, the entire circuit diagram has been given. Using the multiplexers and the select signal, okay, by enabling the select signal, you can force the D flip-flops to go to any state you want. So there are 4 D flip-flops. By making, say, this by making this seat 3 equal to I'm making this seed 3 equal to 1, this seed 2 equal to 0, this seed 3 equal to 1, this seed 3 equal to 0. You can make the starting state to be 1 0 1 0. Means you can load it to any state at any point of time. You can also reset it to any at any point of time by this asynchronous reset signal. Okay, this is basically connected to an asynchronous reset signal. But one problem with this circuit is that it can be proven mathematically as well as by simple logical reasoning. That if you keep the this select signal to be 0, which means all the muxes are disabled. Disabled in a sense that you basically let 0 the 0 data inputs to come to the input, which is always coming from output of either another flip flop or an XORing of some of them. If you enter the state 0, okay, so the state diagram of this thing, this 4-bit state machine is something like this. If it enters the state as 0, okay, say after a reset signal, forever it remains on S0. However, this is not 15 counter because it has all the 15 non-zero states it can cover in some sequence. What is the sequence for this particular state machine? The sequence is this: 1111 to 1110 to up to this. Then it continues, and again after 1110, it comes back to 111. So basically, the state diagram has two disconnected components. One is S0, then S7, and autonomously without any input it can go to no, sorry, it is not S7, sorry, it is S15. It can go to S7, then to S3, and up to this is 14, back to S15. This type of LFSRs, which for n flip-flops can go through all the 2 power n minus 1 non-zero states, starting from one non-zero state. These are called maximal length LFSRs. Not all LFSRs are maximal length. Depends on how you have connected these flip-flops. Usually, the maximal, whether it will be a maximal length or not, there are mathematical descriptions of these LFSRs in terms of polynomials. And if those polynomials satisfy certain properties, only then it becomes maximal strength, otherwise not. However, you don't need to bother so much about so much complication of this in this assignment. The circuit has been completely given to you. The first problem is very simple. It gives you the complete structural description of the state machine. It has drawn the circuit diagram for you. What you need to do is you need to implement a flip-flop module, which is positive edge triggered with positive reset. Instantiate 4 of them. You need to design a multiplexer, 2-to-1 multiplexer module, instantiate 4 of them. You need to instantiate an 2-input XOR gate and just connect them properly. So this is an entirely, this thing can entirely be done by a structural design. Of course, it is hierarchical because you have three different types of modules combined to have the entire circuit. But it is not very difficult because the entire structure has been given in front of you. Even the names of the internal wires have been suggested, names have also been given. Okay. The seed variables at the top, seed 3, seed 2, seed 1, and seed 0, these variables together constitute a 4-bit value that defines the initial non-zero state. So this is one circuit where although you have a reset signal, you should not ever activate the reset signal. Rather, use this seed signal to initialize it to this initial state 1111. After that, it will just let it run for 15 clock cycles. It will go through this transition. That is what you should verify in your test bench. So your test bench is very simple. Just initially set this value, then make the select signal 0 so that the multiplexer does not take any external value anymore, and let it run for 15 clock cycles. And you should observe this, exactly this state transition. Okay. Any question about this, students? Hello?
No, sir.
Fine. Next, the next two state machines are classic state machines design. You must have solved it many times. One is a 2's complement converter FSM, which keeps on reading numbers from the LSB side and keeps on outputting each bit it reads. Either it keeps it unchanged or flips it to generate the 2's complement of a complete number. So let me just go through the algorithm once. So what is the scheme? Very simple. Two's complementer FSM. The principle is that say you have a number, well, let me select something, say 8-bit number 0, 1, 1, 1, 0, 1, 0, 0. Somebody asks you, give me the 2's complement of this. This was a positive number, its 2's complement will be negative, but it can be a negative number also, and you can generate its 2's complement. What is the algorithm? Okay, copy all zeros from LSB side. Copy first one from LSB side. Flip all other bits. So how do you calculate the 2's complement of this? I copy all zeros, 0, 0. Then this is my first one, this one. So I copy that one also. After that, I just flip. And of course, the algorithm or the procedure is completely reversible. So if you if you apply the same on the 2's complement itself, you are guaranteed to regenerate back the original number. So I copy 0, 0, 1, then I flip all other bits, and I get back my original number. Very simple. So this suggests the following design of the state machine. What I need to detect here, student, what do I need to detect here in a state machine? Where does the change of state happen? Because see, initially it just copies whatever it sees. At what point a change of state happens that it starts to flip values?
The first one from the right side.
Right. The first one from the right side is the distinguishing factor which determines the state change. So initially, I am in a starting state, say 0, and this I can reach by reset. And then if I get a 0, I self loop. Okay. And I keep on outputting 0 because this outputting 0 is basically I'm copying the 0 that I have seen. When I see the first one, I move to state says 1 and I copy it that one also. So output is again 1. So I am designing a milli machine. Okay. So remember, this is a milli machine. And then when I reach S1, now my behavior changes. Now, if I find a 0, I output a 1. And if I find a 1, I output a 0. Any question about this? So basically, it's a two-state FSM. Is 1D flip flop. Okay, I mean, this, it cannot be any simpler than this. Okay, it's a one flip flop design. So this is one of the assignments. You reset it initially. Any number of bits you select as input. Okay, remember this. The only thing is that this cannot handle uh, uh, the more than one bit input at a time. So remember, this state machine has one input bit. Your test bench should have a multiple bit vector. Okay, to kind of give the proper which is basically one bit at a time is input to the state machine. Fine. Any question about this, students? Hello, can you hear me?
Yes, sir.
Yeah. Any questions? Very simple state machine. I think all of you know this. So, okay. So I assume you understand this. Now let's go to problem 3. Problem 3 is a multiple of 3 detector FSM. This is slightly more complicated than problem 2. Okay. Uh, First of all, it reads the numbers from the MSB side. So let me again, I am pretty sure you know, all of you know this, but still just to refresh. So I now try to design a multiple of 3 detector FSM. What is this? Well, it works something like this. It can take an arbitrarily long input number, consider it as unsigned. Say, for example, it reads the number 01101, something. It starts reading the numbers from the MSB side and moves to the right. Okay. So this behavior is slightly different. I mean, completely opposite to uh, the behavior of the one's complementer circuit. And this is a detector circuit. It does not operate on the initial value and try to change it. Okay. Now, because it can read an arbitrary number of bits, its behavior at the output is, it denotes the number of bits seen till now. What I mean by that is that, say, if your number is 0110, it starts reading this. So the first character it has read is 01. Then when it reads this, it considers that as if it has read these 2 bits, and its output will denote up to how much it has read. up to that point. Next, it will again move beyond and it will reach 3 bits. So up to when it reaches up to 011, it says, I have detected this number is divisible by 3. But that is not the end of the story, because it has another 1 bit to read. When it reads 1 more bit, okay, it kind of says, no, now this number, yeah, this is still divisible by 3. But if it reads say 1 more bit, then the number probably no longer remains divisible by 3, etc., etc. So the behavior is not, well, it is slightly peculiar in a sense that its decision continuously changes. There is means it, see, in DFA design you have an accept state, whether the string is accepted or rejected. Okay. Here this guy's behavior is similar to the pattern detector that we have seen. That it can enter the accept state, but then again it can go out of the accept state depending on further information that it brings. Fine. So let us try to draw the state diagram of this. I will not draw the complete state diagram, but at least try to do something. First of all, how many states does this need, students? So how many cases do we need to differentiate, first of all?
Three cases.
3 cases, right? So I denote state S0 as that number is 0 mod 3. S1 number 1 mod 3. And S2 number is 2 mod 3. That's it. So I require 3 states and I require 2 flip-flops. I require 2 flip-flops. Sufficient. Now let's try to see the behavior of S0. What does S0 mean? S0 means that number must be of the form CM for some. Do you agree that it is of the form CM? So S1 similarly denote that the number must be of the form CM plus 1. S2 number must be of the form CM plus 1. Now suppose I have read certain bit string, whatever. Suppose this is the number. Okay. What is the change in the number? Say I call it the new number prime that is being read. When I read a further bit, B after. So now my number prime includes what is the relationship between number prime and number? Up to this I have read. So the thing is, up to this I had read, then I read further 1 bit more. This B is a binary quantity, either 0 or 1. So number prime must be equal to 2 multiplied by number plus B. Do you agree with this, students?
Yes, sir.
Fine. Now, so consider this is the fundamental principle, and then you start say 0. So now instead of number, I am writing n equal to 3n. Okay, 3m. Okay, when I read one more bit, n prime becomes 2 into 3m plus b, which is 6m plus b, which is, there are two cases. If it is 6m plus 0, if your b that you have read is 0, this is 6m, that is S0, it remains in S0. If it is 1, it is 6m plus 1, that is it goes to S1. So my state transition for S0 looks something like this. Incidentally, this is itself the accept state. Okay, because when you reset and it starts from 0, you have read 0. 0 is divisible by 3 trivially. So the start state, unfortunately, or not unfortunately, just because of the peculiarity of the problem, it itself the accept state. Anyways, if it reads a 0, it self loops. It has one output to show whether the output, whether it is divisible by 3 or not. So it makes the output 1 and it self loops. If it receives 1, it is goes to S1. S1 denotes numbers which are not divisible by 3. So the output becomes 0. Now what about S1? S1 is of the form 3m plus 1. So n prime, when another bit is read, is 2 into 3m plus 1 plus b, which is 6m plus b plus 1. Two cases, b equal to 0, it becomes 6m plus 1. B equal to 1, it becomes 6m plus 2. 6m plus 1 is S1, 6m plus 2 is S2. So if it gets 0, it self loops. If it gets 1, goes to S2. And similarly for S2, please work out what will be the state transitions. Okay, so for S2 also you can, where n is of the form 3m plus 2, n is between. Any questions? Students, any question about this? Hello?
No, sir.
Okay. Everything is crystal clear. Okay. Very good. I will have a look at the quality of the Verilog code that you write then. Because theoretically, because you have understood everything. Okay, S2 I can complete. Okay, so N2 N prime will be 2 into 3m plus 2 plus b, 6m plus 4 plus b. So b equal to 0 is 6m plus 3 plus 1, that is S1. And b equal to
I
1
think you're
is,
not sharing your screen now.
oh, okay.
This is
Wait,
slides.
can you see now?
Yes, sir.
Yes, sir.
Okay. So for S2, n equal to 3m plus 2. So the change value when you read one more bit is 2 into 3m plus 2 plus b. Uh, yeah, so 6m plus 5 is 6m plus 3 plus 2, which is S2. something is wrong here. I must have messed up somewhere.
In S1, the
Yeah,
enzyme will.
S1 I think messed up. I think I have messed up because this will be
So
6m
if
plus b plus 2.
b equal to 1 will go to S naught.
Yes, it has to come back to S naught. Otherwise, it can. It will never come out of state. Yeah. So bad mistake. Uh, it will be 1 and 1. And what about S0? S0, what about B equal to 0? B equal to 0 is 3m plus 6m plus 2. So this will be S2. This on 0, it goes to S2. And for S2, it can go to S1. And if it receives 1, it self loops. Yeah, so it will be something like this state diagram. So please just verify. It is not difficult state diagram in this. And we have just now seen a pattern detector complete solved example, which essentially is very similar to this, right? Uh, you will require 2 flip-flops, 3 states. In fact, the pattern detector was more complicated state machine. It required 4 states. Here I can do with 3 states. Okay. The assumption is that when I have not read any part of the string, that for the null string it accepts, which is fine. I mean that's okay. Without any information about the string, it accepts it is divisible by 3. Could have designed it in a different way where the reverse assumption would have been made, but then you would have to do more. Here, because the starting state has become the accept state, it is kind of declaring even null strings to be divisible by 3. Now, I mean, it has no information about what is the binary string, but it says it is divisible by 3. It's okay. Any questions, students? Anybody has any question about this? Oh. Students, anybody has any question?
No, sir.
No, sir.
Fine. Let us move to then the problem 4, which is the biggest problem and the most complicated problem if you try to do it by hand. But if you do it using Verilog, shouldn't be that difficult. Okay. So this circuit takes two 32-bit numbers A and B. These 32-bit numbers are stored, pre-stored into 32-bit registers. These 32-bit registers are special registers which have parallel load capability, where you can initialize the registers at any value using a master load signal or something. This type of registers, flip-flops, you must have read in your codes or the circuit we showed in example 1 is basically that you can load any state you want in the register. Now this shift registers shift on the left on every clock cycle, and the value which is on the output is applied to the sequential comparator. These are unsigned, these are considered to be unsigned numbers. So there is no concept of negative number, everything is positive. So suppose one bit of A and exactly the same B is 1 and exactly the same bit of B is 0. Immediately you know that the number A is large. There is no need to compare the rest of the number. Okay. That logic is implemented by this circuit. There are three output signals L, E, and G, less than, equal to, and greater than. And this will require, actually this we had said as an exam problem to solve by hand in last year's, I think mid-sem or somewhere, maybe last year or previous year. There you needed to solve it by solving Carnot maps. Here we are asking you that design the circuit without going through this painful exercise of solving Carnot maps for LEGs, etc. Just go through the exercise so that you write Verilog and it gives you the correct functionality with the compiler taking all the burden of correctly synthesizing and optimizing the circuit for you. So this particular exercise is to kind of show you the power of Verilog. Okay. This is slightly complicated because you need to think of the control signals that are used. There is also some op and other control signals. There is a clock control signal. Okay, the comparator, etc. Also, the clock signal also controls the shift registers. Okay, so these shift registers have clock signals which have not been shown. Okay, so they have clock signals also. They are controlled by clock signals. It is not shown. Read the specification, this specification, in very carefully to understand how it works, and then implement it by writing its behavioral description of this LEG part. Okay, whether to show, which shows whether the number is less or equal or greater. Just if you write the behavioral specification correctly, your compiler will guarantee that the circuit that you generate finally is correct. Okay, so these shift registers you need to implement them any way you write. In the slides, there are examples of ring counters and shift registers. So you can use the behavioral example. So very, very easy. Just need to describe one shift register and instantiate it twice. The skill lies in describing the correct case state, probably a case statement based block for these LEG signals. Okay. And at the end, after 32 bits have been processed, uh, uh, it kind of that these values make any sense actually, because these values might keep on changing as you keep on reading more and more bits. Okay. For example, if your A is a number 0010 and your B is a number, I'm not showing 32 bits, I'm showing 4-bit numbers. If B is a number 0001, you know that this number is large. Why? Because first it starts Because first it starts reading these values. It has no information. So these numbers look to be equal because the bits are equal. Then it reads these two values. It still has no information. Because, well, till now, whatever it has read, 00 and 00 are exactly the same. But then when it reads these values, because this is 1, immediately it declares, and this is 0, immediately it declares that A is greater than B. There is no need to compare these two values. Okay, so this is how the circuit works. It is not essential that you will need to keep run it for the entire 32 cycles. Although here the assignment has been simplified to say that okay, we'll run it for the entire session till the entire 32 bits have been read. Okay, and initially the machine is in reset state. Reset signal has not been shown, and the shift registers. So this is a FSM. Okay, this FSM has to be designed. This is a sequential comparator. It's not a combinational comparator. And this also has a reset signal, which has not been showed as mentioned. And these shift registers can have reset signals, but more importantly, they have asynchronous load capability. Or in it is called a parallel load capability, this type of shift register. Where at any point of time, it can load any non-zero value to the flip-flops. Load the initial. When that control signal is enabled, this flip-flop 32 flip-flops will be loaded with the correct values, the values numbers that you want to compare in your test bench. Okay, so in your test bench, you can have 3 cases where A is greater than B, A equal to B, and B equal to A, and A smaller than B. To show all 3 are working, of course, they will require, each of them will require 32 clock cycles. So you need to design the state machine which keeps on reading 1 bit at a time, and it's a simple state machine, because once you have decided that A is greater than B, you need not go back to any other state. Okay? And I believe this probably will be a Moore machine. Just make sure. Very simple state machine. Although the assignment problem looks bombastic, it has several blocks, 2 shift registers, 1 sequential circuit, but overall it's not very difficult. I think the state machine will have only 2 or 3 states, and you can solve it quite easily. Any questions about this?
Sir, one thing.
Yes.
Sir, for this one, we are using the shift registers for the input. Can we do the same for the 2 and 3?
Yeah, you can use shift registers for 2 and 3.
Okay.
But there is one slight, I won't say it's wrong, but there is one slight issue. See, 2 and 3 never mentions the length of the input numbers. So they work for arbitrarily long input numbers. So there should be no feature in your design which has a dependency on the length of the input number. You make a design which does not work for only 8-bit numbers or 16-bit numbers or 32-bit numbers. But the moment somebody says, I want a 35-bit number, you say, no, this design will no longer work. Why? That is wrong, because that is not there in the spec. The spec for the problems 2 and 3 says they should work for arbitrarily long numbers. And that's the design of the FSMs, right? Did you ever mention the length of the input string? No, nowhere did I mention. In the last problem, yes. Last problem, it is given that it's a 32-bit number, so you can use 32-bit shift register. So my suggestion is that you use shift registers in your, you can use shift registers in your test bench. Okay, for 2 and 3. Don't make it part of the main design. Your main design should only be the FSM. In your test
Okay.
bench, you can instantiate shift registers. Of course, your shift registers have to be defined somewhere. So they will eventually become part of your design, but don't make it part of the FSM itself. FSM is here also. The FSM is separated from the two shift registers, right? And you will find that this FSM also, as far as I remember, there is no feature of this FSM which says that it cannot work for anything other than 32. It can work for any arbitrarily long number. Here we have specified 32, right? So you can, yes, you can use shift registers for 2 and 3 also, but be careful that there should be no dependency of that on any of the FSMs of 2, 3, or 4 problems on the length of the shift registers.
Okay, sir.
Anything else, students? Do you want me to give you a tutorial on Verilog? Say Friday class, do you want to attend a tutorial on Verilog? Just a general tutorial on Verilog? Hello? Hello, are
Yes,
you
sir.
there?
That would be fine.
Yeah. So what is the consensus of the class? I mean, what do the majority think? Only if the majority thinks a tutorial is necessary, I will give a tutorial. Otherwise, I won't give a tutorial because tutorial has already been given. I mean, if you want, I can give. Otherwise, what do you want? Yes, no, you cannot say. If you are confident, no point repeating. I will teach from a I will teach it in a slightly different manner. But first of all, you need to say that it is required.
Sir,
Yes.
sir, write a comment and then people can upvote. Means for
What?
consensus. You can write a comment and then people can upvote. Means like the comment too. Then you can decide whether the majority wants it or not.
Let's have a tutorial on Friday, okay? Let's have a maybe a 2-hour tutorial on Friday because now I mean now the from now onward the Verilog assignments will be like these are becoming. I mean next week probably there will be even more complicated assignments. So next Friday, today's class is more or less done. Next Friday, let us have a couple of hours of tutorial, okay? Between maybe 2 and 4, 2 to 4.
Yes.
I have a meeting at 4, so anyways, I have to leave before 4 on Friday. But let's have the tutorial, okay? So please attend Friday's class for the tutorial. Start solving the assignment. Enough background has been given. Okay, I mean, for today's assignment, I don't think it is possible to give any more explanation. Okay, enough explanations have been given about the problems, the general Verilog design principles for FSMs, the mathematical properties that are necessary, how to come up with the state diagrams, everything step by step has been described. So I hopefully you will be able to manage. Okay, so Friday let us meet for a 2-hour tutorial and continue with the assignment now. Okay, so I'm stopping the recording. Thank you.